What are the odds of rain? So how do we go? So basically we're converting, chances mean probability, huh? So we're converting from probability to odds, right? We talked about probability and odds. So remember, probability is 4 over total, where odds is 4 colon against. Or you can put the word 2 in the middle, or whatever. So the two numbers for a probability are 4 in total, and for odds are for and against. That's the only difference between probability and odds. So what you want to do is take that 30% and turn it into a fraction, huh? Because, you need it to be that way. So 30 over 100, does that make sense on that? 30%. You know what the word percent means, right? Per 100, cent. How long is a century? 100 years, right? So percent means per 100. Like if you say, hey, I was watching the baseball game, 20,000 people, and 30% of the crowd was wearing hats at the ball game. What does that mean? 30 per every 100. If you could spread out the hat wearers evenly among all the whatever 1,000 people, and then break them into groups of 100, there'd be 30 in every 100 that are wearing hats. So that's what percent means. Question?
Wait, what's the word in the top of the fraction?
4, right here.
4?
Mm-hmm.
FOR4?
FOR4. Yeah, so the amount that are for something. Yeah, so if you're flipping a coin, the chance of heads is 1 out of 2. One result for you out of 2 results possible. So for probability, it's 30 per 100. 30 like what you want to happen per 100. Now reduce that fraction. That's 3/10, right? So it's 3/10 when you reduce that fraction. So the amount for, so that's how I get the 100, right? Because it's 30%. That's why there's 2 zeros in the symbol, like that, because it's the number 100. And that's why there's a divide bar. It means divide by 100. That's what that symbol's telling you, percent per 100 over 100. Okay, so it's 30 per 100. So 30 per 100 reduces to be 3 per 10. So the probability is 3 per 10. That's 4 over against. So how do we change that to odds? Well, again, odds is 4. No, whoop, I did the wrong thing there. It's 4 over total. Probability is 4 over total, and odds is 4 and against. So odds is like a debate. I was thinking about it like a debate, right? People are at odds. They're having a debate. So whereas probability is just 4 over total people in the room. So they start the same, don't they? They both start with the same number, the 4, the amount that are for you. And then the against, if there's 10 total in the room and 3 are for you, 7 must be against, huh? So it's 3 to 7 or 3:7, however you want to do that. Does that make sense on that? So you always want to go to fractions when you convert between odds and probability. That's probably what got you, huh? If anybody, whoever missed it, the 30%, changing that, realizing you need to change that to a fraction. That's probably the trick. So always change to fractions when you're going to convert between odds and probability on that. Good? All right. Did you make it through all that homework? Chapter 15's done, right? We're in we only have one more chapter to go. And tomorrow's our practice exam. Thursday's our real. Okay. So we have this bell-shaped curve thing. It says, consider the normal distribution shown to the right, and assume that P is a point of inflection of the curve. Complete parts A through C below. Find the mean, median, standard deviation. Okay, let's talk about this bell curve. Basically, this whole chapter is about this bell curve thing. So it looks like a bell, for obvious, that's why the name. It looks like a bell. It's called normal distribution because it's how things are normally distributed. That's just what it means. It's also called the Gaussian curve because Carl Friedrich Gauss is the one who came up with it. It's got another name, isn't it? The normal curve, Gaussian curve, bell-shaped curve, hey, whatever. Probably come to me. Anyway, it's very, very, very well used. It's got all these different names. So what is it, first off? Let me first off just give you an example of what it is. If you were to measure anything that occurs naturally, say like the weight of leaves off the trees out in the grass area around here. If you picked all the same kind of tree, whatever those trees are, I have no idea. You're just like to grab all the leaves, and then weigh them. They'd be very light, but you know, on a real sensitive scale, weigh them all. What you would find is you would find some average weight, right? I don't know what. Let's just make stuff up here. Maybe 10 ounces is probably too heavy, but anyway, whatever. Say the average weight of the leaves is 10 ounces. Okay, you would find most leaves are right around the average, whatever that is. And then now some leaves weigh more, some weigh less, but there's not as many that weigh more and less. Like some of them go up to 11 ounces, and some go up to 12, and some go down to 9 and down to 8. But there'd be a hump in the middle. Basically, the hump in the middle, bell curve, normal curve. You'd find that you'd have more leaves that are right around the average, whatever that average is, and some are real big and some are real small. If you went and you said, I'm going to measure the length of people's pinky finger, and you just took everybody, 1,000 people, and you measured the length of their pinky finger, you might find, I don't know what, 4 inches is the average, or I don't know. There's some average, and most people would be kind of close, a little bit more, a little bit less, close on average. There'd be some long, some with crazy long, I don't know, basketball players, whatever, super long pinky fingers, but there wouldn't be many of those. The curve would come down, and there'd be some people with really, really short pinky fingers, but there wouldn't be many of those. You'd find it humped in the middle again, bell curved. If you measured, you get the idea, right? Women's shoe sizes, men's weights, heights of pigs in the whatever, any naturally occurring phenomenon, anything you want to grab is going to be normally distributed. It's the normal distribution we find. Bell curve, meaning most things are average, whatever that average. You get a big, in other words, it's not even. You ever thought about that before? That it's not even? Like, let's take something you're more familiar with. Women's shoe sizes. How about that? What's the average women's shoe size? 8? Something like that? I'm guessing. Anyway, 9, 10, 11, I'll just make stuff up here. 6, 5, whatever. So it doesn't go like this. Right? Let me make sure that makes sense. I don't want to just draw curves and have it not make any sense to you. If I was to grab all 1,000 women and have them write down their shoe sizes and make a big graph, I would not find the graph goes straight like that. In other words, there would not be as many women with a shoe size 12 as there are with a shoe size 8. Would there? There'd be a few with shoe size 8. Very big feet, but not a lot of those. There'd be much more, it'd be humped like this, wouldn't it? There'd be much more around the average. It wouldn't be same amount have shoe size, 3 as have shoe size 8. No, there'd be a few with super tiny feet that have shoe size 3. But most would be around the average, whatever the average is. So things occur that way, don't they? Things are spread out. You ever thought about that? The way things occur in nature, the naturally occurring way of things, is there's an average for any of these things. And most things are close to the average. You get a few really big and a few really small, but it drops off real quick, doesn't it? So that's the bell curve, the Gaussian bell-shaped curve. And so they just, science uses this in all kinds of arenas for anything occurring naturally. So they use it, and they use some statistics that go with it. Let me show you those statistics. Erase all them bell curves. Okay, so first off, they're asking us some basic questions. Find the mean. Mean just means the middle, huh? There it is. You can see the middle of that curve is 83. That's just a gimme. Boom. Median, same thing. I mean, that's a freebie, right? Mean, median, whatever you want to call it, it's the middle. It's the middle of the curve. It's the average, whatever this is. If this is, I don't know what that is. Find the standard deviation. Now, remember what standard deviation is? I don't mean like all the steps for calculating. We're not going to do that. I just mean, what is it? What is the feel of? That's more important, because you will read studies where they mention standard deviation. It's good to have a feel. That's average distance from the middle. Average, remember, to deviate means to be different than normal, right? A social deviant is one whose behavior is different than normal, right? So standard deviation is average off the normal, average off the middle. So when we talk about standard deviation, what that is, that's the first jump here. So that's the standard deviation is how far from here to here. That's the standard deviation. Remember, deviation is distance from the middle. So How far is that? How far is 98 from 83? Well, you just subtract them, and you get whatever that is, 15, and there's the answer for the standard deviation. Now, what does that mean? And we'll get into that. But for now, that's all they want you to do, is subtract those two numbers. All right, I'll move on to number 2. Getting us warmed up and comfortable with the standard normal Gaussian bell-shaped curve. Find the median again. Oh yeah, well actually they're not telling us. So they're giving me 78 and 66. And I found, there's the answer you're looking at, but how did I find that? How did I find the middle there? How could I find the middle of 66 and 78? Exactly. The middle of two things is the average, isn't it? So the average, wait, it's jumping on me. Here we go. So the average. So I'm going to take 66 and 78 and average them. Add them up and divide by 2, and that's where I got the 72. It's the middle, so the middle is 72. Let me go back and put that on there. Right there, the middle is 72. Now they want me to find, on part B, the standard deviation. Remember that, what that is. That's how far from the middle, first jump to the right or the left, you can go either direction. How far from the middle to the first jump to the right? Well, looks like 6, doesn't it? 78 minus 72, 6. 6. Next question. Find the third quartile of the distribution. I'm just going to give you a formula for that. We're going to use it quite a bit. So Q3 is mu plus, oh, I got to tell you what those things are, huh? 0.675 sigma. Mu, that's a Greek M. It kind of looks like a U with a little squiggle on the side. It means the mean, the middle. And this little circle thing with a little thing on the top there is called sigma. Well, you don't care what the Greek thing is. It's the standard deviation. I'm not going to quiz you on the names. Standard deviation. So yeah, so there's middle and standard deviation. Now there's the jump, the gap. How far from the middle to the first jump. So those are the symbols we use. We use Greek symbols. So this is a Greek lowercase m, a Greek lowercase s, basically. So mean and standard deviation, m and s, mean and standard deviation. So Q3, the third quartile, is the middle plus 0.675 times the standard jump, the standard deviation jump. So, okay, so it's the middle. What's the middle? 72. Plus 0.675 times the jump amount. What's the jump amount? 6. So if you work that out, you'll get whatever I got there, 76. If you round it to the nearest inch, if you round it off, you get 76. Joseph?
How do you get 0.675?
Yeah, it just, I'm just giving you the formula. Yeah, I didn't derive it or come up with it. I just copied it out of a book, basically. Yeah, so just write that down on your 3x5 card. It's 0.675. We'll just use that every time. So that's for Q3. Q1 is almost the same thing. It's mu minus 0.675 sigma. So let me just write them both up here. So here's the formula you want to put on your 3x5 card for the exam on Thursday. Q1, the first quartile, is mu minus 0.675 sigma, and Q3 is mu plus. So they're both from the middle, right or left, 0.675 sigma. 0.675 times the standard deviation. Is that good? Is that making sense? So you want to have these two on your 3x5 card. We'll use them a lot. And be thinking of it anytime they refer to like 25% or 75%, think, oh, they want me to do Q1 or Q3, first quarter, third quarter. They'll be sneaking that in on us. And so we'll just pull out that formula, those formulas, whenever we need them. Is that okay? So they're saying mu is 81.7 And Q3, third quartile, is 95.2. And they're saying, hey, can you find sigma? See over here, they want sigma. Can you find sigma? So just use that exact same formula we just used. Which is what? It's Q3 equals mu plus 0.675 sigma. So just use that formula. Plug in your Q3. Plug in your mu. And solve for sigma, kind of like you'd solve for an x. You know what I mean? You guys have your calculators? Can you solve that little equation there for sigma, just like pretending it's x, you know? Doing a little algebra. Get the x alone, get the sigma alone. Here's the wall. So the little sigma is saying I want to be alone, right? That's what I always tell my algebra students. Sigma wants to be alone. So subtract 81.7. Remember how that works? Remember from algebra? Subtract that from both sides. And then we get something. 13.5 equals 0.675 sigma. Like that. And then the last step to get, what is the last step to get sigma alone there? What do we do?
Divide 0.675.
Exactly. Divide by the 0.675. We all good with that? And so sigma will equal, is like 20 or something? 20 exactly? Okay. 20 exactly. Remember that? Remember that kind of algebra stuff? Questions I can answer for you on that? All good. All right. I'll keep moving. So how did I know I need to do all that? They gave me Q3. That was the key. They gave me Q3, I think. Oh yeah, get the Q3 formula. To me, it would be very boring if it didn't connect to anything in the real world. Okay, and this does. This is very, very much real. Consider the normal distribution defined by the figure to the right. So first we just got to learn the tools, and then we'll do the real life stuff. Find the mean standard deviation of the distribution. Yeah. Find the mean, find the... Yeah, can you do that one? Just like the last one, right? Find the mean, find the standard deviation. So use your calculator, see if you can do that. So how do you find the mu, the mean? We have to take the middle of those two, huh? So just add them and divide by 2. 47 plus 63 divided by 2. So that's 110 divided by 2. 55. So that's the middle. The middle is 55. Now, how do we find the sigma? What's the sigma? So this is the middle is 55, right here, 55. So what do we do to find the sigma? Remember what sigma is? Jasmine, do you want to say something? Right. Correct. Count from the middle. Yeah, because that's what it is, huh? Yeah, it's how far from the middle to the first jump. You can go right or left, either way. Yeah, so what it is, what standard deviation is how far from the middle, first jump right, or first jump left, either way. It's the gap from the middle, one jump right or one jump left. I keep talking about one jump. I'll show more jumps in a minute. So, so let's do that. So it's 55 minus 47, or you could do 63 could do 63 minus 55. Either way, you're going to get 8, and 8 is the answer. The gap from the middle, right or left, is 8, in other words. Does that make sense? It's 8 either way. 8 is the gap. It's the standard deviation. It's the average distance from the middle. Is that good? All that? Is that making sense? Now, I don't know if it bothered you, but we did not use that 68% at all, huh? I'll explain why a little bit. We'll explain why in a little bit, but we didn't need to do anything with it. It actually told us that we could do all this stuff, but I haven't told you there's times you can't, so we'll see. Okay, so looking at this one. Now, this time they're saying, can you find the middle? Can we find the middle? Let's do that first off. You know how to find the middle, right? No problem at all. The middle, we just grab these two numbers, add them, and divide by 2. So 73.25 plus 82.75 divided by 2. The middle of that must be the 78, I guess. 78? Okay, that nothing new there. But now the next part is going to be different. Y'all feeling alert? This fools people, this next part. Fools them right, left, and every which way on the exam. I don't want it to fool you. Pay attention to what's happening now. Okay, the middle is 78. The middle is 78. So let me just stick that in the middle here. Middle is 78. Now, you might think, they're asking for the standard deviation, right? Which is the jump amount. You might look and go, well, we just did that 3 or 4 times. What's the big deal? It's just the jump. It's just the jump from here to there. Just subtract them. No, not this time. Well, how do you know? It was only, bless you, it was only last time because they told me this was 68% of the data. You see, let's go back. When you have the full normal curve, you realize if you're going from the middle, one jump to the right and one jump to the left, that captures 68% of the data. Just because somebody draws a curve for you and says, here's the middle and here's some other spot, that doesn't mean that's necessarily exactly one standard deviation to the right. You with me? I know they've been doing that. I know these ones. You go, yeah, it was here. It was here. I know it was. It was. You know why it was there? There was they didn't give me the 68% here. I know. What they told you is inflection point. Inflection point. See how they call this an inflection point? What an inflection point is where a curve goes from bowl down to bowl up. Have you ever heard of that in higher math? A point of inflection, a curve inflects. What I mean is, look, doesn't this look like a bowl turned down right there? Right? And then right here, doesn't this look like a part of a bowl turned upward? Right there, they connect. Same thing right here, they connect. See where the bowl turned up and the bowl turned down connect? That's called a point of inflection. The graph inflects there. It goes from bowl down to bowl up. Right there, that point is called a point of inflection. Well, the point of inflection is at the first jump. So that's another way. So they can tell you, hey, this is the first jump to the right in 2 different ways. Just because they put a line there is not enough. Are you tracking with me? Are you getting the big idea? Because this is what people think. People look at the picture and they go, well, if they're giving me a line to the right, that is the first jump. Not necessarily true, which we'll see in this example now. Just because they draw you a graph and put the middle and put a line to the right, you cannot assume automatically, unless they give you some extra information, that is exactly one standard deviation jump. No. There could be, if I just do a curve, if I just go, yeah, here's a curve, there's the middle, and I'll put a line here. There could be like 2 other, that could be the 3rd jump. I'm just showing you this one only. You know what I mean? That could be not even to the first jump yet. Who knows? Just because I show a particular line they got to give you extra information to let you know exactly what that line is. Is it 1 jump? Is it 2? Is it part of 1? What is that line? And there's a couple of ways they can do that. They can tell you it's a point of inflection. Well, then that means, yeah, it's exactly 1 jump. Where the curve goes down to up, that's exactly 1 standard deviation. So point of inflection is exactly 1 standard deviation jump from the middle. So that's one way they can say it. Or they can tell you that 68% of the data is between the two jump lines, because that means it's exactly one jump to the right and one jump to the left, remember? Remember when I drew the curve a minute ago? And I said there's the middle, and the first jump right and the first jump left always have 34, 34. So if they tell you, hey, these two are making 68, then yeah, that's for sure one jump, one standard deviation, ST, standard deviation. You with me? I want to write that out. One standard deviation jump right. It's got to be, if it's 68% of the data. So there's two ways they can tell you. They can say, hey, there's 68% of the data captured in there. Well, then they're saying, hey, that's exactly one standard deviation jump right and left to the middle. Or they can say, hey, it's hitting at a point of inflection, bowl up, bowl down right there. Well, then, okay, that's exactly one standard deviation jump to the right. But if they don't give you those two, you cannot assume. And so that's what's happening. That's what's happening here. In fact, let me put it on a fresh. Well, no, we're good here. Yeah. See, they're not telling me this is a point of inflection. See, they never say that. And they're not telling me this is 68% of the data. They never say that. So this, in fact, is not one jump to it. The first jump to the right is somewhere past this or before this. I don't know. They're not showing me. They're just marking some spot and saying, hey, what's that spot? Are you tracking with me? A lot of the battles I'm trying to undo in your mind the assumption that you can just assume that's one jump. Right? You can tell it'd be wrong. If I subtract 82.75 minus 78, I'm only going to get 4.75. I'm not getting the right answer. See, it's not right. Is that good? Okay, so well, then what is right? So if that's not right, how do you do the problem? Well, what are they telling me? What are they telling me there? 75% of the data. They're saying all that blue shading, it's 75% of the curve. What should we do when we hear 75% or 25%? Q1, Q3. Q3 for 75. They're telling you about Q3. That's what they're telling you about. Did everybody see how we dialed in with that? They're not telling me 68%. They're not telling me inflection point. If they did, then that would be one standard deviation jump. Instead, they're telling me 75% of the data. So if they say 75 or 25, they're telling you about the first quarter, third quarter. Right? If I said I'm watching the football game, I'm 25% of the way through, I'm at the end of the first quarter, right? Or I'm 75% of the way through, I'm into the third quarter, right? They're telling me that. They're telling me these are quarter marks. That's what these are. These are not one standard deviation marks. These are quarter marks. That's what they are. So I got to use the quarter formula. Well, which one? You can actually use either one. If this is the middle, this is halftime, then the one before it, the quarter mark before it must be Q1. The one after must be Q3, huh? That's exactly what they are. You can do either one. This is Q1, this is Q3. Use either formula you want. I'll just use Q1. Q1 is what? Mu minus 0.675 sigma. So Q1, which is, now I can't read it, 73.25. So plug that in for Q1. 73.25 is mu, 78, remember that's the middle, 78 minus 0.675 sigma. Now solve that equation for sigma, like solving for x. That's how we do that. You could have done the Q3 formula instead. Doesn't matter. Either one would give you your answer for sigma. Everybody see how I came up with that and how I recognize that? It's the 75% that keyed me in. So let's solve. Let's subtract 78. And so we get something minus 4.75 is minus 6.75 sigma. Last step in solving. Divide by minus 6.75. I mean, minus 0.675. And somebody got an answer there? Oh, I guess it's the 7.04, right? Yeah, it looks like 7 to me. 7.04? That coming out, which is what we have here. So that's the standard deviation. Those are quarter marks, not one standard deviation marks. We're able to use those quarter marks to find out how much one standard jump is. So one standard jump is 7, so it's actually a little further than these marks, huh? Right? One standard jump is like a little past this and a little past that. How do I know? Because it's 7. It's 7 from the middle. Add 7 to 78, and you get, what do you get? 8, like 85. It's like at about 85. It's a little past those marks. Those are just the quarter marks. Anyway, we don't care. We don't have to do anything with that. We're done. Questions on that? Is that okay? So you see 25 or 75, do the quarter mark thing. They want you to do the quarter mark thing. You see 68 or inflection points, then they're just using one standard jump. All right, I'll move on if you're okay. This is about this normal curve, this bell curve. It's very, very useful in real life. All right, normal distribution. That means when you read that on the exam, normal distribution, you think bell curve. That's the normal way naturally occurring things are distributed. Has standard deviation. They give me the sigma, and they're saying 84% of the data fall above 48.1. Okay, so let me help with that. Let's draw a curve. Yeah, what you're going to need to do is basically draw a new bell curve with every question. And you, of course, want to put one bell curve on your 3x5 card, that shows 3. So there's the middle, and there's 3 jumps to the right, 3 jumps to the left. There's the middle, 1 jump right, 2 jumps right, 3 jumps right, 1 jump left, 2 jumps left, 3 jumps left. So, and then the percentages, right? The percentages are always the same. 34, 34, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15. Okay. So what? What does all that mean? Okay. So let me go ahead and erase. I mean, it's true, but we don't need all that in the bottom. Okay, so one thing I want to try to help you with, because they're going to throw a lot of numbers at you on these bell curve problems. The percentages go, notice all the percentage numbers go up here in the curve. And the non-percentage numbers, like the 48.1, see, he's not a percentage. So where's he going to go? Bottom line. Does that make sense? So that 48.1 is going to go somewhere on the bottom line. Well, where? How do you know where? Well, what does it say? What does it say about so the 48.1 is somewhere. It's at one of these lines. The 48.1 is. Well, how do you know which one? Well, it says that not 84% are above it. Above means to the right, right? Below is left, above is right. So there's some kind of, what if I told you, here, let's play around with the curve for a minute. You just want to get more and more comfortable with this thing. If I said, hey, I'm going to put my finger somewhere, and I want to put my finger along the bottom so that to the right of my finger is 50%, let's say. Well, that'd be the middle, huh? If I stop my finger in the middle, then to the right of my finger is 50% of the curve, half, of course, right? What if I put my finger right here on this line, 1 to the right? What percent of the curve is to the right of my finger? Well, I don't know, whatever these add up to be. You can just add them up, and that'd be the percent to the right, huh? Right? What if I stop my finger right here on this first line to the left? What percent of the curve is to the right? Well, more than half, because 50% is from the middle, plus 34, what percent? 84, that's our spot. Do you see that? Do you see that? Right here must be that 48.1. Why? Because all of this is 50%, it's half the curve. You can add them up and see it's got to be. You add all those up, it's 50% and 34%, right? To the right of this line is 84% of the curve, isn't it? It's 50 and 34. It's 84. That's what they're talking about. So this must be 48.1. 48.1 is the spot on the bottom that has 84% above it, to the right of it. 84% of all the, whatever it is, men's weights are more than 48.1. That's not right, but anyway. Right? And, okay, so what? So what? Well, what do they want? They want the middle. Where's the middle? Here. Well, how do I find the middle? Well, they're telling me how much the standard jump is. They're telling me each of those lines is 9.3. So I can say, oh, okay. So this is something, if I add 9.3 to that thing, what do you get? 0.4, 17, 57.4. This must be 57.4. Yeah, that's what it is. 57.4, because, right, if you subtract 9.3, you get back. So I just added 9.3 to go to the right. Every line, between every line is 9.3. That's what that standard deviation means. It's the gap from line to line. The standard deviation gap from line to line. Question?
I can't read, what's the percentage it gives?
84. Yeah, 84%. 84% above. It says 84% are above to the right. Well, that one. Is that good? Does that make sense how we came to that? So they give you the percentage. You find the spot that has 84% to the right. That's 48.1. You know the gap from line to line is 9.3. Add 9.3. And we got the middle. So they're just making sure we're comfortable with this curve. That's what they're going to do. Just kind of throw it at us in all different ways. They're going to get real here in a second. Can I leave that one? We good? Let's see. What percent of the data fall below the value mu plus sigma? So here I can write this bigger. Percent of data below means to the left, doesn't it? To the left. Of mu plus sigma. That means 1 sigma, right? There's not another number there. So that means, hey, if you have the bell curve, wasn't a very good one. If you have the bell curve, and you're going 1 jump to the right, 1 to the left. So here, this spot is mu plus 1 sigma. What percent is all of this? That's what they're asking in part A. Right? If you're at mu plus 1 sigma, you're at the middle, 1 jump to the right of the middle. You're right here. What percent is below, is left of you? Well, remember what the percentages always are? Yeah, it's 34%, and then all the rest of them, but I don't need the other ones, right? Okay, normal distribution has a mean and a standard deviation. Approximately what percent of the data fall between boom and boom? That's a weird question. Okay, well, we'll see. So basically, when you read these questions, just make the normal curve, Just always make the normal curve. That's always what they want you to do. Or unless they say like 25% or 75%, then you just use the Q1 or Q3 formula. Is that making sense how to approach these? Basically, if you read the question and you see something in there that indicates first quarter, third quarter, 25%, 75%, something like that, then just pull out those formulas. Otherwise, if they just start talking about means and standard deviations and percentages, just draw the bell curve. It'll all come from the bell curve. So just every time you're just drawing that bell curve. So I'm just going to draw. I really don't know what they want me to do yet, but it'll all come as I draw the bell curve. So draw the bell curve. 1, 2, 3 jumps to the right of the middle. 1, 2, 3 jumps to the left of the middle. And the middle. Now, what do I know the middle? Yeah, they told me the middle. 12.4. Can you all read that? 12.4 is the middle. And the sigma, that's the standard deviation. That's the jump from line to line. So the jump from line to line is 3.1. So let's do this. So I'll take that 12.4 in the middle, and I'm going to do what? I'm going to add 3.1. So that would be 15.5, and add 3.1 again. What's that? 18.6, and add 3.1 again. What's that? 21.7. Good, and then I'll just subtract the other way. I'm racing ahead of you. Give you just a second. Get caught up there. Subtract your 0.1, so it can be 9.3. Yeah, and then subtract 3.1. Going to be 6.2, and then subtract 3.1. going to be 3.1. Good. So I put the middle on there because they told me the middle is 12.4. Then I just added 3.1 3 times to the right and subtracted 3.1 3 times to the left. And you know the percentages, those are always the same. Those are 34. So notice the numbers on the bottom change from example to example, but the percentages never do. Y'all seeing that? So when somebody says something is normally distributed, they mean the percentages are what they are. You know, these percentages is what it means to be normally distributed. Okay. All right, so now what's their actual question? What percent between 3.1 and 21.7? There's their actual question. So what percent is between 3.1 and 21.7? Well, now we see it. Here's 3.1, and here's 21.7. So we just add up all these percentages. Does that make sense? You know what the easier way to do would be? Take 100% minus the 2 that are missing. Because the whole curve's 100%, right? Either way's fine. You get the same answer. I'm going to take 100% minus the 0.15 minus another 0.15, which is 0.3, so it's 99.7%, which indeed is the answer. Almost all the curve, 99.7% of the curve is in that region. Is that good like that? So what did I do? I read it. There wasn't any quarter stuff, so I just said, all right, I'm just going to do the normal curve. So I just put the middle. They gave me the middle. Then they gave me the jump amount from line to line, standard deviation. Just add 3.1 3 times, subtract 3.1 3 times. Then I just wrote in the percentages that are always the same for every normal curve. In fact, it's what it means to be normally distributed. You mean you have those percentages. So I wrote them in there, and then I just found my 3.1. And my 21.7, and I just added the percentage in between. Actually, I took 100 minus the 2 edges that were missing. All right, we're done with the section. That's good. As an engineer, I remember, you know, I don't know if you think I just pop out of the room. I just always loved math. Math was hard work for me, too. And I was taking what I thought was going to be my last math class. And then I realized I didn't like engineering, and I changed to math. So then I had more math, obviously. All right, so same thing, more bell curves. 2,500 students take a college entrance exam. Scores in the exam have an approximately normal distribution. In other words, bell curve. With mean, middle, standard deviation, 9, middle 56, standard deviation is 9. Use the 68, 95, 99.7 rule. That means the percentages in the bell curve. I'll show you where they're getting. I already told you the 68. The 99.5 is the next two. 99. We just saw the 99.7, right? That's what those are. That's 1 jump right and left is 68. 2 jumps right and left is 95. 3 jumps right and left is 99.7. That's what that is. That's bell curve talk. That's bell curve talk. Estimate the average score on the exam. All right. Well, the average. Question A. What's the average? Well, that's 56. They gave that to me. Nothing to do there. Question B. What percent of the students scored 56 points or less? Well, half of them, because that's the middle. It's like a silly question, huh? Right? It's like that old. Have you seen that old saying? They say, it is shocking to know that 50% of the population is below average. I mean, it's obviously, that's what it means. The average is the middle. That's basically what that question is, right? 50% are below the middle because that's what it means to be the middle. Right? So anyway, all these questions, before I go any further, let me just draw the bell curve. So really, I don't even need to write that in. Let me just draw the bell curve. Let's do that. So the bell curve, the middle. What is the middle? 56. They told me the middle was 56. And then 3 jumps to the right of the middle. And 3 jumps to the left. And how far from jump to? They told me the middle is 56. And they told me the sigma, the standard deviation jump, is 9. So from line to line, it's 9. So 56 in the middle. And then you add 9, add 9, add 9, subtract 9, subtract 9, subtract 9. So add 9, so that 66 minus 1, 65. I'm just going to add 10 and subtract 1. Be 75 minus 1 is 74. Add 10, 84 minus 1 is 83. So add 9, add 9, add 9. Subtract 10 before it says 47. 37, 38. Subtract 10, 28, 29. Like that. We good? Okay. So now, and what are the percentages? Those are always the same, right? The percentages never change. The numbers on the bottom change, whatever you're measuring, women's shoe size or men's weights or whatever. There's some average, and then there's some standard deviation jump. That changes from example to example. But the percentages are always the same. 34, 34, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15. Okay, so now I'm ready for their questions. Here come their questions. What's the average? Yeah, well, we already did that. That's the middle, 56. So that's the average. B, what percent scored 56 or less? What's the percentage that way? Well, 50%. Can you all see that okay? And then what percent, I've got the answers filled in already, score between 47 and, 47 and 65. Well, 47's right here. And 60, so the numbers you see, or the numbers they give you, should show up down here, other than the quarter marks. If they give you some number that's not down here, it's a quarter mark. That's the only other thing they can do. And if it's to the right of the middle, it's a third quarter mark, because that's after halftime, right? If it's to the left of the middle, like if they said, hey, where's the number 63? I'd go, 63? I go from 56 to 65. I don't got any 63. Then I'd go, oh, third quarter. That's the only other thing they're going to do to you. So if they give you some, see how they're telling me 47 and 65? And those are marks on my graph. But I'm telling you, if they give you some number, which they will in just a few minutes, they'll give you some number like 63 or something. You go, well, I don't got a 63. Remember, quarter marks. If it's some number that's not down there, it's always a quarter mark. And if it's to the right of the middle, it's quarter 3, because it's after halftime. If it's to the left and they give me like 48 or something, I'd go, oh, that must be the first quarter mark, Q1. So that's the only thing they can do on it. That's all they will do in this chapter. They'll either give you one of your direct lines or some other number, and that'll be Q1 or Q3. All right, let's keep going. So 68, now what percent are between 47, between 47 and 65? Well, 47, 65, 34, 34. 34, 34. 68%. That's easy, right? And now, last one. What does part D say? 65 points or more. 65 points or more. How many scored 65 or more? Well, here's the 65 line. More are these three. That's kind of getting scribbly. 13.5%, 2.35. So it's whatever that's. It's. Oops. Write it down over here. It is 13.5% plus 2.35 plus 0.15. Choose your calculator. 16%. We're done. Did you track with that? Part D asks, so this is some exam. By the way, this is real. SAT, other college exams, they are almost always normally distributed as well. Not just like physical things, but like these kind of things, so many things are. So no, there'll be some average score that people get on the exam, SAT or whatever. There'll be some average, and most people will be, close to the average, and then some people will be super genius people, and some people will be not so good on it. So, but they'll be most middle. You know, be humped in the middle, bell curved, humped in the middle. Most people are average at everything. You know, most are average. There's always a few outstanding. There's a few that are really low, right? On that. Does that make sense on that? How that works? Yeah.
Wait, how again did you get the 34% and then the makeup of the percentiles?
Okay, so you mean how did I get these percentages that I'm writing up here? Yeah, those are just those are just what it means to be. Those are the same on every example, and they're what it means to be normally distributed. So you just want to put that in your 3x5 card, and those never change. So you want to have that. That's the definition of the normal curve, is those percentages.
Okay.
Does that make sense? Yeah, so you always want to, 34, 34, 13, 5, 2, 3, just those are always the same. Every example, it's in fact what it means to be normally distributed. It's the normal distribution we find. It's the Gauss curve thing. So those always change. Those never change. The numbers on the bottom are the things that change. From example, this could be, men's weight, pounds. It could be women's shoe sizes, inches, or whatever that is. Right? So that's the bottom numbers totally change. Percentages never change. So question D asked then, so this is how the test went. That means the average person on this test got a 56. Right? And then some people did way better, some did way worse. Approximately what percent of the students got a score of 65 or more? Because that's a good score. So here's the 65 or more. 13.5, 235, 0.5. So you add up these percentages, and right, because I did 65 or more, so I added up those three percentages right here, 13.5, 235, 0.15, and I got 16%. So 16% of the test takers got that score or more on that. Does that make sense? Is that good? I can't help but think. Try not to get too far off topic, but being different than normal, high percentage. I enjoy watching sports, especially. I like pretty much all sports, but I like sports where the individuals play, because you realize you're getting people that are so far off the normal. It's just amazing to watch their talent. Like tennis, I'm into tennis, and just watch they just finished Wimbledon. Think about those tennis players like Federer, who just won again. He is amazing to watch. His ability to control the ball, his hand-eye coordination is just unbelievable. Because even compared, and I love baseball. I'm a Dodgers fan. Sorry if you're a Giants fan. I'm enjoying this year. But really, the baseball players, there's 500 of them out there. Maybe they're the best 500 baseball players in the world. Still, that doesn't compare. If you're only number 500 tennis player in the world, you're nobody. You're nothing. The tennis, when you watch Wimbledon, those are the best, top 10 tennis players, in the world. That's on the percentile scale. They are just crazy off the charts. They can do things with the ball that is just like they're an alien. I don't know if you've ever seen, there's this funny little video. You can I don't know if anybody's a tennis fan. You can type in Roger Federer, commercial thing. They showed this one time. He was shooting a commercial with somebody. In the middle of the commercial, he was goofing around with the guy. And he said, hey, you want to see something funny? Put this can on your head. So it's showing his ability to control the ball. So this guy looked a little nervous, and he's like, okay. He's like, put this Coke can. It was like a Coke can. All right, just stand right there. Stand right there. And he had the tennis racket. He was in the middle of the commercial, but somehow they had it still filming. And the guy stood there. He said, just don't move. And he threw the ball. They were in a room, and he just hit it, with his tennis racket. Just took the can right off the guy's head. Didn't touch his head, at 100 miles an hour. I mean, it's just amazing. The skill. Anyway, so I just appreciate. So percentile, these are people off the charts, and it's just fun to watch. Athletes that are just off the charts. Normal distribution. Number 2, 2,500 students take a college entry, same kind of thing. Scores, and here's how you're going to recognize it on the exam day after tomorrow. Approximately normal distribution. So that's okay, bell curve thing. There's the middle, 57. The middle is 57. Standard deviation, 13. Middle is 57. Standard deviation is 13. So, You know, I wouldn't even read any more of the questions right now. I would just start drawing the curve. It's just what you've got to do on all of them. So I'm just going to draw the curve. So Journey, you're a big soccer player. Can I embarrass you? Or can I just ask you a soccer question? Journey and I talk soccer because my daughter's into soccer too. So we had a big conversation, speaking of percentiles. We watched the Pele movie in our house maybe a month ago. And we were debating whether Pele, if he was young and compete now with who's the big phenom now that's won 5 years in a row.
It's either Messi or Ronaldo.
Yeah, Messi. I don't even know the other one. So would Pele be better than Messi as far as an overall skill? What's your opinion, Journey?
I don't like Messi.
You don't like Messi? Okay, what don't you like about Messi?
I don't know, I'm a big fan, I'm a Madrid fan, so I like Ronaldo.
You're a what's that?
A Madrid fan.
Oh, okay, so I'm not even up on it. I don't know what that means.
Yeah, so I like Ronaldo, but
Okay.
I don't know, I just personally don't like him.
Okay, okay. We were watching, I mean, it's amazing what that guy can do with the ball. And of course, it was amazing what Pele, anyway. I'm just impressed with all of them. Anyway, just amazing skill. Yeah, my daughter was, my soccer player daughter was like, no, Pele couldn't beat Messi. No, anyway, that was her opinion. All right, so the middle is 57, and we're going to add 13 for every line. So the percentages are always the same. You just take the middle, and you just add the line amount to the right and to the left. Okay, so add 13, what's that, 70? Add 13, what's that, 83? Add 13, what's that, 96? So pretty much the same in all these examples, right? Just pop down the middle, add the standard deviation amount right, and subtract it to the left. Minus 13, 44, minus 13, what's that, 31, minus 13, what's that, 18, thank you. 18, and then the percentages are always the same. So I'll write those in there again. 34%, 34%, 13.5, 13.5. Going to have them memorized here pretty soon, I bet. Okay. Okay, now I haven't even looked at a question. Oh, you know what? I should have. I'm sorry. I'm wasting your time. I should have looked at the question. Sorry, guys. It says first quartile. You don't need to draw all that. Yeah, I'm sorry. Forget that. You don't need all that on this one. So it's a rare day, but every now and then they'll just ask for a first quartile or third quartile. All you need is that formula. Sorry. Just all you need is Q1. Remember the formula I gave you a bit ago? What was that? Mu minus 0.675 sigma. Yeah, sorry. You don't need it. I should have read the question. That was bad. I just assumed, but that wasn't good. All right. Probably talking too much sports. I'm getting sidetracked. All right. So Q1 is mu. So what's the mu? What's the average? 50. Yeah, all you gotta do is plug into this formula. This is a nothing problem. And I was making it more than it is. Just plug into that formula. Does that make sense? Just plug in the mu, plug in the sigma, like that. And then hit the buttons on your calculator. I don't know, is it I guess the answer's right here, 48.2. And then for the Q3, again, just use the formula. That's mu plus. In the Q3 and Q1 form is the same, just plus and minus in the difference, right? Because quarter 3 is to the right of the middle. It's after halftime, right? And quarter 1 is before halftime. It's back before. So mu is 57 plus 0.675 times 13. And that is, I guess that's the 65.8, like that. So those are easy. You don't need the bell curve on that one. Just Q1, Q3 formulas. Good. Let's keep moving, get through these. Before I draw that old bell curve again. Let's see, okay. Part of research, blood pressure, blah, blah, blah. Blood pressure is also normally distributed, it's true. Have an approximate normal distribution, standard deviation. Okay. Estimate the number of patients. Yeah, same thing. So it's just draw the bell curve again. Let's do it. I think it's valuable. So let's draw the bell curve. It's exactly what it is. Like that, the middle. Maybe I should give a little more room there. Let's do that. So there, like that. So the bell curve, the middle is going too high because I can't read the question. I'm just going to have it like that. There we go. So the middle, one jump to the right. So here's the middle. One jump to the right, two jumps to the right, three jumps to the right, one jump left, two jumps left, three jumps left. The middle, they're telling me, what are they telling me? The middle, the mu is 127, so put that right in the middle. And the standard deviation is 13. The sigma is 13, so you add 13. So that'll be 140, 153, 166. Does everybody see what I did there? I just put the middle down and I added 13 every time. And then to the left, I'll subtract 13. Right? And subtract 13. 12, what's that, 88? Yeah. Okay, the percentages are the same every time. So I write those in there. 34, 34, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15. Okay, so now, what are the questions? Approximately 2,520 patients. Oh no, I came up with the answer. So they're asking, how many, how many patients had a blood pressure 114 or higher? So they want to know 114 or higher. So it's interesting. We can figure out all kinds of questions just from the knowledge that blood pressures are normally distributed, which I'm sure they are, and the average and the standard deviation, the jump from line to line. So, because all these percentages are always true for every normal curve. Okay, 114 or higher. Well, look for the 114. There it is. 114. Or higher. Higher means which direction? To the right. So they want all this, don't they? 114 or higher. What's the percentage?
84%.
Can you tell right away it's 84? Because it's half the curve and 34 more. It's 50 and 34. So you don't, I mean, you can add all these up in your calculator if you want to. But an easier way is to say, look, from the middle over is half and then 34. So it's going to be 50% plus 34%. It's going to be 84%. But they did not ask me percentage. If they did, we'd be done with part A. They didn't say what percentage of patients. We need that. That's still important, but we got to do one more step. They said how many patients. How many? So what do you do when they say when you have a percentage, but they're asking how many? What do you do with that percentage?
Percentage of the total.
Of the total, huh? So it's 84% of the 3,000. Up here, they said this is a graph of 3,000 patients altogether, right? Yeah, 3,000. So I've got to take 84% of this is 3,000 patients and all their blood pressures from the lowest to the highest. So I've got to take 84%, which you know that means make a decimal, right? 0.84 times 3,400, and I guess that comes out to be the 2520 number that we got right there. Oh, can you read that down there? Yeah, it's in the Doseri thing.
So isn't it 3,000?
Well, it's 0.84 times the 3,000, and then that comes out 2520, I think. If you multiply 0.84 times 3,000. Yeah, because 3,000 is the whole thing. It's like all the curve. And so this is just this is just 84% of the curve. This is most of the 3,000 people. But it's not these people. These are the other people, the other part of the 3,000. So 2520. Does that make sense? Question B. How many patients had, so question B, let me change the color. So question B says 114, between 114 and 153. Between 114 and 153. Okay, so what percent are between 114 and 153? Well, it's from here to here. Right, see the numbers there? 114, 153. So just add those percentages, huh? 34, 34, 13.5? They just want percent? Oh, they want how many? So I'm going to have to get the percentage and go times 3,000. Okay, because that percentage of all the patients of the 3,000 times the 3,000. So what's that going to be? 34, 34, 13.5, 68, 78, 81.5% of the 3,000. Right? So let me run out of room here. That's the 114. So I'm going to take 0.815 times 3,000, which will equal to 2,445 patients have blood pressures between 114 and 153. Is that good? Is that making sense there? You okay with that? So whatever they ask, like in question A, how many patients 114 or higher? So I found the 114, right? And 114 is not a percentage, so it's a number down here, right? Percentages are up here, numbers that are not percentages are on the bottom. So 114 or higher, that was 84. It was 50 and 34. It's 84% of 3,000 times 3,000. And the next one between 114 and 153, just add up those three percentages. 81.5, so change it to decimal, 0.815 times 3,000. 2445. Good. We good with this? Just normal curve, normal. Packaged foods sold at supermarkets are not always the weight indicated on the package. Variability always crops up in the manufacturing and packaging process. Suppose that the exact weight of a 24-ounce bag of chips is randomly variable. It's approximately 24, standard deviation, blah, 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 blah. What are the chances? Okay. Yeah, and this is true. You know, manufacturing processes, they set machines to dump certain amounts in bags of chips. You know, I mean, chips in bags. And but they're not exact, right? They do the best they can. And the machines have some variability. Sometimes they'll give a little more. Sometimes they'll give a little bit less. And that's part of what, you know, quality control people look into, is how the variation is going with all kinds of processes. So especially making cars, Japan did a lot of really good things, and we don't have time for a big story about all that, but they use this math. This is a lot of why manufacturing improved. Somebody named Deming showed them how to do a lot of stuff. Anyway, maybe I'll talk about that later. Let's get through the homework. So what are the chances the bag weighs between that and that? So I'm going to do the same old thing. It's just another bell curve. The machine does not exactly the same thing every time. There's variability. Why don't the machines do the same thing every time? Lots of things affect it, like temperature. If it's hotter, metals expand. If it's colder, metals contract. And so the amount they grab changes. Now, they try to regulate that inside factories. They try to regulate humidity levels and things like that because they know things will change, and they're trying, especially for car makers, they're trying to make it exactly the same every time so it'll fit with the other parts of the engine, right? So these kind of things are used a lot in manufacturing, having, you know, less variability, real exact processes. So 1, 2, 3 jumps to the right, 1, 2, 3 jumps left. So we have the center, 3 to the right, 3 to the left. What's the average on this one? It tells me the average is 24. So I'll put 24. I think they're going to have a wrinkle on this one. Are they? We'll see. So I can't tell. I'm trying not to just do the same thing every time. But there are some curveballs coming. I just can't remember which one. This might be the curveball. There's a few curveballs coming. This might be one of the curveballs. So 20. That's a 24. And then how much is the jump? 0.75. So the sigma is 0.75. So that means this is 24.75. This is, what's that, 25.5. And this is, what, 0.75, so 26.25. And then this is down 0.75, so 23.25. And this is, so 22.5. And this is 0.75, so 21. I can't do it. 21.75? Yeah, right. Okay. I think those are right. So I just put the middle on there, 24, and I just added 0.75, 0.75, 0.75. I think that's right. And I subtracted 0.75, 0.75, 0.75, like that. All right, let's find the, and you know the percentages are the same every time. Let me take their question. The chance that a bag weighs between 22.5 and 25.5. So where is that? 22.5 here, 25.5 here. So remember the percentages? 34%, 34%, 13.5%, 13.5%. So in other words, what that means is they're saying if this machine that's delivering the chips in the factory, it on average drops 24 ounces of chips into a bag, but it's never perfect. Temperature, humidity, things like that change, and sometimes it does a little bigger bag, sometimes a little less, right? 34% of the time, it's, you know, between 24 and 24.75 ounces, and, you know. So what's the chance it's going to be between 22.5 and 25.5? Well, you would just add up these percentages. Just add those up. That's how I got the 95%. If you come on up to here, if you add 13.5, 34, 34, 13.5, it equals 95%. That means there's a 95% chance that 95% of the bags are going to have chips who weigh between 22.5 and 25.5 ounces. Usually it's going to be in that range. 95% of the time it's going to be in that range. That's what that means. Good to there? Does that make sense? Part B, the chance that a bag weighs between 24 and 25.5. 24 and 25.5. Well, that's not really a big deal. These are all pretty easy. 24, 25.5, that's 34% and 13.5. And that equals, what's that, 47.5. That's part B. Right, we good with that? And then part C, the chance the bag weighs less than 25.5. Yeah, so these are all standard. No curveballs here. Less than 25.5. So part C. Less than 25.5 is right here. Less is all those percentages. How do I figure out all the percentages less than 25.5? What's the quick way? Oh, you could. Yes, right. You could add these two, subtract from 100. Or you could just say 50 and these two. Right? I always like that half the curve is 50 thing. Right? So I could say, look, it's 50% of the curve, which is all this. Right? 50% of the curve. And then these two sections, which is 34 and 13.5, which is 84, 94, 97.5% of the curve. So 97.5% chance you're going to get 25.5 ounces of chips or less. That's what that means, if that's how the machine cranks things out. Is that good? We good on that? All right, it's a lot of normal curves. I know we got 15 minutes to go. We're doing well. So that, okay, this will be slightly different. So okay, so they're giving me baby girls' weights at birth. So the average is 15.75. Standard deviation is 3. So I'm going to draw another curve. Here we go again. Another bell curve. The middle. The middle is 15.75. 1 jump, 2 jumps, 3 jumps to the right. 1 jump, 2 jump, 3 jumps to the left. And it's, so the middle is 15.75. The sigma is 3. The jump from line to line is 3. So I'm going to add 3. 18.75, add 3. 21.75, add 3. 24.75. And then the other direction, I'm going to subtract 3. So at 12.75, subtract 3, 9.75, subtract 3, 6.75. Good, same old thing, put the percentages in there, those are always the same. 34%, 34%, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15. Okay, there are the percentages and the numbers on the bottom. Okay, now here come their questions. A 9.75 pound baby girl is in the what percentile? How did I come up with that? 2.5th percentile. Do you remember what percentile means? Percent, let me write it up here. Percentile means percentage to the left, or percent below. So you want to remember, percentile is not exactly percentage, it's percent below. It's percent to the left. So that's what percentile means. My first baby girl, Emma girl, was born and she was at the, I don't know, below 1 percentile. So what does that mean? 1 percentile, not just percentage, 1 percentile. The doctors told me, and I knew what that meant. What did that mean? Really light, right? In other words, less than 1% of baby girls have lighter weight than her. She was super light. I don't know why. I mean, she's normal, and in fact, we always had little light babies. And so she's my lightest. She's still very small. And but they thought because she was so low, this is why doctors use this all the time. Because if you're really weird one direction or the other, they suspect there's something wrong. I mean, that's normal. They should, right? They should look. So Emma was so light, she was below the 1%. I don't remember what her weight was. She was healthy. I mean, she was all the way to full term, and everything was normal. But she was so light, they didn't do anything right away. But like at our first 3-month appointment or whatever, the doctor checked her out, and I think the doctor accidentally nicked her or something like that because there was just a little bit of blood, but it made the doctor freak out. And it was a young doctor. It was a new doctor. She was kind of young, and Emma was below 1 percentile. So the doctor was thinking there might be something wrong with this baby, And then I think she nicked her. Somehow later she said she nicked her. Anyway, she found a little blood in her urine or stool right there. And so she went, I think there's a problem with your daughter. You got to go to San Francisco. We had to take Emma girl to San Francisco, where they have all those sad kids that have all those really, really hard things. It was a sad place, all those little kids. And just put her through all the tests for everything under those special machines. She's crying over it, Babies don't like all that. Anyway, but she was completely healthy. I was very thankful. And I was happy the doctor was all apologetic. I was thankful she was careful. But anyway, so percentiles, so it means percent below. Percent below. That's why doctors always use that, so they know if you're average or you're way off average. So percentile means percent below. So when they say 9.75 pounds, 9.75, there's the 9.75, and they say percentile, they mean percent to the left. So this one and this one, huh? Does that make sense? So you want to just know percentile. You want to write that in 3x5 card. Percentile is percentage to the left. So you would just go to 2.35 plus 0.15 equals 2.5%. So a baby girl that was born at 9.75 pounds would be at the 2.5 percentile, meaning only 2.5% of all baby girls have lower weight than that. It's very rare to be that low. It happens, 2.5% have even lower, but it's rare. You're pretty light. That's what that means. All right, so question B, a 21.75 pound baby girl, that's certainly a bigger baby girl, a 97.5, is at what percentile? Again, percentile means percent below. So 21.75, it's right there, huh? So what percent below? That means all of this. Right? Percentile, again, means percent below, percent less. So, if you're at 21.75, what's all the percentages below? Well, again, I'm going to do the 50% thing. Half the curve is 50%, and 34 and 13.5. Does that make sense how I'm doing part B there? So, 21.75% below percentile equals 50% plus 34 plus 13.5, what's that? That's the 97.5. So if you're born at the, baby girl's born at 21.75 pounds, she's at the 97.5 percentile. That means 97.5% of all baby girls are born with weight less than that. So most are below that. You're pretty high on the scale. Finally, question C. Is that good? Like I'm just talking at you? Telling you stories every now and then. You guys are just all taking it all in. All right. So question C. Baby girl, 75th percentile. What should I do? Remember what you do when you see 75-25? Yeah, Q1, Q3, that's Q3 formula, huh? Right, so again, so I just want to key you because they'll suddenly throw that curveball at you. If you see 75-25, you think, oh, quartile formula. Not these numbers anymore, forget about the chart. Q1, Q3 formula. Whenever they do the 75-25 thing. So what is 75? I'm kind of running out of room. Let me maybe come up here or something. 75 percentile means 75% left or below. Remember, percentile means percent below, doesn't it? So if I was watching a football game and said, I'm at the 75 percentile mark in the game, where am I at? 75% of the game has gone on before. I'm at the third quarter, right? I'm at the third quarter. That's Q3. That's Q3. So they're basically saying, hey, Q3, what's Q3? That's what they're asking. Find for me Q3. So Q3, what's the formula? It's mu plus 0.675 sigma, right? And so, and I just plug them in. So Q3 is mu, the middle, 15.75. Plus 0.675 sigma. What's sigma? I forgot already. 3? It's 3, right? Yeah, 3. So that comes out to be 17.8. We good there? Does that make sense? It's 2-hour straight lectures. You guys okay? Am I doing the Charlie Brown teacher voice? Wah, wah, wah. I do try to tell stories every night just to make sure you're awake. Can I tell one more? Journey, I was embarrassing again. She played soccer here. I don't think it's embarrassing. I think it's great. Played soccer here for Fresno City for 2 years. I took my little daughter's 10, my youngest daughter's 10, Abigail. I took her it was about 2 years ago. You're probably playing. It was about 2 years ago. I took her and her other little soccer friend to one of your guys' games. You guys were doing really good that year. You were near the finals or getting real close. Was that 2 years ago when you had a really good season?
Yeah, we did both years.
Both years?
Yeah.
I thought last year wasn't as good as the year before. Is that true?
Last year we got to it, we just didn't we went farther the year before, but we got to it too, but we just.
Oh, okay.
Yeah.
But further 2 years. Yeah. Because, you guys got real far. Anyway, so I went to one of those games, and I went there with my two little girls. It was right after soccer practice. They had their uniforms on. I went there and watched, and I loved it. I thought it was super exciting, but these little girls are just, I don't know if all little athletes are this way, but they could watch for a little while, but then they wanted to do something bad. Or just something active. They were running around like crazy. I'm like, anyway, so I was ignoring them. They were like 8 years old. And then all of a sudden, I'm trying to watch the game, and it's just me, I don't know, or my wife or somewhere else, and I was watching the game. All of a sudden, I look down, and Abby's little friend, Grace, she just put something in her mouth real quick, from the ground out there in the cement, and it looked like it was a little bug or something. And I'm like, Grace, what are you doing? What are you doing? And I said, what do you have in your mouth? She goes, she's a little smell, an ant. I'm like, why are you eating? And then she quickly swallowed it real quick before I could get anything. And I said, why did you swallow an ant? And she goes, because Abby did. She pointed, which is my daughter. I'm like, Abby, why'd you? That's what they do. I don't know if you was that way as a little soccer player. They just compete constantly. I can swallow an ant. I can hold my hand in the ice bucket longer than you. Anyway, that's what my daughters did the whole time when you guys were out there playing. That's true. Let me write this in here. Okay, so so there's a formula for that. If I can find it here. Here it is. So let me give you the situation we're talking about here. For what's this called? A random, let's just call it a random event, like rolling a die, flipping a coin, that kind of thing. The average, the mu, the middle, the average, will be n times p. What is n? Number of times. N's always number of times in all of our formulas, huh? P is the probability of whatever it is you're doing. So if it's flipping a coin, probability of heads is a half, 0.5. If you're rolling a die, the probability of getting a whatever you want, a 6, is 1 in 6. You know, it just depends on what you're doing at the moment. So we're doing it for flipping a coin on this one. So the mu, the middle, the average number of heads, will be the number of times you flip the coin, they said 6,400, times the probability of getting the heads each time, 0.5, so just like we said, 3,200. 3,200 is the average number of heads you're going to get. I want to make sure this is real for you, because you'll do much better with it if it's real. So that's that answer to part one. Real life, what would happen? I mean, just real life. If you could just flip a coin, if everybody did it, we added them all up, so it's 6,400 flips, a lot of flips. We would think we're going to get about 3,200 heads, but we probably wouldn't get right on the money, 3,200. We might get 3,210. We might get 3,000 just below it, you know, whatever, 3,190 or 93 or, you know, we'd get close, wouldn't we? We'd get close to 3,200, but we wouldn't probably get right on the money. Now, we wouldn't get far off of that, would we? You sense it, right? You sense the random way things work. You're not going to get like only 1,000. No way. There's just no way. You could do it for the rest of your life. You could flip that coin 6,400 times every day for the rest of your life. You're never going to get only 1,000 heads. I can show you the probability. It's virtually impossible. It's more likely to be struck by lightning 3 times on the way there. It's that hard. This is what's interesting about probabilities. There is an average, and we think, yeah, but it's just random. It's just random. Anything can happen. Well, it's random, but it's not likely that anything, right? I mean, to think about, what if I took the coin? I said, could I flip 10 heads in a row? Is that possible? It's possible. Sure, it's random, but have you ever done it? Do you know anybody that has? You know what the chances of flipping 10 heads in a row is? I can tell you, it's actually not hard to figure out. It's 1 in 1,024. It's 1 in 1,024. So you flip the coin 10 times in a row. You do that 1,024 times, probably one time, you'll get 10 heads in a row. So my point is, even though probability, I think probability is very interesting because even though it is random, it's random with a pattern. You ever heard of the saying, scientists talk about this a lot, order in chaos. Have you heard of that? That's kind of like what we're talking about. Coin flipping, dice rolling, right? It's all random. It's all random. Yet there is predictability in the randomness, right? General predictability, not exact predictability, but general. So that's what we're talking about here. There's an average number of heads, yeah, but you're not going to get exactly that. You're going to get close to that. And then there's a standard deviation. Let me give you the formula for standard deviation. Standard deviation is the square root of n times p times 1 minus p, all in a square root. That's the amount you're going to be off of the middle. So what's that? Then that's the square root of n. N is 3,200. P is still 0.5 times 1 minus 0.5, which is the square root of, whoops, I'm running out of room here. Let me bring it up here. So it's the square root of 3,200 times 0.5 times 0.5. You guys have a calculator? Well, I did it already. It's 40. Yeah, can you get that in your calculator? So make sure you know how to do that in your calculator. Square root of 3,200 times 0.5 times 0.5. Everybody see why I got the 2.5s? Not just one? Because the formula is np1 minus p. So it's n, 3,200, p, 0.5, and 1 minus 0.5, which is 0.5 again. So if you multiply, so I would just probably start with the 3,200 times 0.5 times 0.5. I think you'll get like 800. No, not 800. Yeah, 800, right? Is the square root really 40? Doesn't seem like 40 to me. Is it 40?
don't know why that seems funny to me all of a sudden. It's not 40, is it? 1600, 800. 40 times 40 is not 800. The answer's not 40, is it? What are you guys getting? Anybody getting this? Oh, what am I doing, guys? You guys got to... I'm just getting tired, I guess. 6,400, not 3,200, right? No wonder. I knew something was wrong. I'm plugging in the wrong number. The end was 6,400, not 3,200. 6,400. There we go. That's 0.5 times 0.5, root it. What's that? 32, 16. Yeah, that's 40. Sigma should be 40. Good, that coming out? Okay, now, just got 2 minutes left here. So what are we supposed to do with that? Well, you know that means bell curve, right? That means a bell curve. This is the middle, 3,200 is the middle. This is the jump from line to line. So I'm going to erase this. Hopefully you got that written down. We'll do more of this next time. Let me just draw this bell curve real quick. So another bell curve, average 3,200, that's the mu. And then the jump from line to line is 40. Boom, boom, boom. So go up 40. So this will be 3240. This will be 3280. This will be, what's that? What's 40 more? 3320. And this is down 40, down 40, down 40. So this is, what's that? 3160, 3120, 3080. Yeah. And the percentages, you know them. They're always the same. Now, I'm running out of time, so let me just say this. What that means is there's a 34% chance you're going to get between 3,200 heads and 3,240 heads. There's a 68% chance you're going to get within 40 above or below the average. Do you see how hard it is to get below 3,000 heads? Remember, I said you're never going to get below 1,000. You're just never going to get below 1,000. No way. It's impossible. Somebody tells you they're lying. There's just no way. 2.35, 0.15. Look at that. Only 0.15% of the time will you get even below 3,080 heads. See how predictable randomness is? That's why I'm always hard on the casino industry. This is exactly what they know. They know all them dice being rolled, all them things being done. They know the predictability and the randomness. They know it quite well. All right, so we'll have to do more of this next time. You just would answer all the rest of the questions like usual. We'll wrap. So this is not due. All that's due is 16.1. We finished 16.1. Due tomorrow. It's tomorrow, Wednesday. So tomorrow we'll finish 16.2, do our practice exam. Thursday's the real exam. Let me get the clicker thing up here. Clicker. Clicker. So... Okay, clickers are open. Click A for Apple. And we are done.